Good morning, students. In today's lecture, we will discuss energy methods. Energy method is a technique to prove the uniqueness of solution for a given initial value problem. So here we will discuss this method for the uniqueness of solution for the initial value problem of non-homogeneous wave equations. So the statement of the theorem is, we have to prove that there exists at most one solution U which is twice continuously differentiable on the closure of ut. This ut is the parabolic cylinder defined by u cross semi-open interval 0 to t. This function u solves the wave equation curl to u by curl t2 minus Laplacian of u is equal to f in ut. With the initial conditions, the value of u is g on gamma t. This gamma t is the parabolic boundary of ut. It is defined by ut closure minus ut. This t is in the base. Next condition is partial derivative of function u with respect to t is h on u cross t is equal to 0. It means when time is 0, then the partial derivative of function u with respect to t has the value h. So we are to prove the uniqueness of solution of this initial value problem. In this problem, capital U, which we have used here, that is open and bounded subset of n-dimensional real Euclidean space. Now, to prove the uniqueness of solution, let us assume two solutions u and u bar for the given initial value problem. We have to show that these two solutions u and u bar are same. U and u bar both are twice continuously differentiable functions on the closure of ut. Now let us define a function w, which is the difference of u and u bar. Now let us find the partial derivative of this w twice with respect to t, and then we find the difference of Laplacian of w from curl to w by curl t2. Now curl to w by curl t2 from here, that will be curl to u by curl t2 minus curl to u bar by curl t2, and Laplacian of w from here, that will be Laplacian of u minus Laplacian of u bar. So we can put the values in this expression. If we put the values in this expression and we combine these two terms, curl to u by curl t2 minus Laplacian of u, and combine these two terms, then we can see that because u is the solution of non-homogeneous wave equation, so this expression is f in ut, and also this expression is f because u bar is also the solution of the given initial value problem. So we get curl to w by curl t2 minus Laplacian of w is 0 in ut. Now let us verify that on the parabolic boundary of ut, the value of w is 0. Now, because we are given that u is g on the parabolic boundary of ut, and also u bar being the solution of the given initial value problem, that will also having the value g on the parabolic boundary of ut. So u minus u bar, that will be 0, and u minus u bar is the function w. So we can say that function w is 0 on the parabolic boundary of ut, which we have denoted by the symbol gamma t. Now next we'll prove that when time coordinate is 0, the partial derivative of w with respect to t, that is 0. Now because u and u bar are the solutions of given initial value problem, and when time is 0, curl u by curl t is h, and also curl t, the partial derivative of u bar with respect to t, that is also h. So their difference will be 0, and by definition this is curl w by curl t. So we have proved partial derivative of w with respect to t is 0 on u cross t is equal to 0. Thus we have proved that the function w defined by u minus u bar satisfies the homogeneous wave equation in ut, and on the parabolic boundary of ut the value of w is 0, and also curl w by curl t is 0 on u cross t is equal to 0. Now let us define energy function, which we have denoted by E, and this is a function of t. It is defined by half of integral of curl w by curl t square plus the square of mod of dw over the set u. Here this t belongs to the closed interval 0 to capital T. Now we are to prove that this energy function is a constant function. So to prove this, we will have to prove that its derivative with respect to t, that is 0. So differentiating this function with respect to t. On the left side, the derivative of e with respect to t we have denoted by e dot. On the right side, having the derivative, this is 1 by 2 integral. The derivative of this term will be 2 into curl w by curl t into curl 2 w by curl t2, and dw mod square means dw dot dw. So by using the product rule of differentiations, the derivative of this term with respect to t, that will be 2 into dw dot dwt. Wt means partial derivative of w with respect to t. We can take 2 common from here and we can cancel out with this 2. So we get the derivative of energy function, which is given by integral curl w by curl t into curl 2 w by curl t2 over the set u plus integral over the set u of dw dot dwt. Now let us find the value of this integral by using Green's formula. According to Green's formula, integral of u into Laplacian of v over the set u is equal to negative of integral of dv dot du over the set u plus integral of curl v by curl nu over the boundary of u. Now here we can compare this expression with this term. So in place of u we have curl w by curl t. So using this formula we can find the value of this integral. So finally the derivative of energy function with respect to t is equal to integral of curl w by curl t into curl 2 w by curl t2 plus integral over the boundary of u curl w by curl nu into curl w by curl t minus integral over the set u of the function curl w by curl t into Laplacian of w. Now let us combine these two integrals under the one sign. So we can write this integral in this form, and this term we have taken as it is. Now because we have already proved that w is the solution of homogeneous wave equation, so this term, that is 0, and also we have proved the partial derivative of function w with respect to t, that is 0 on the boundary of u, so that term will also be 0. So we have obtained derivative of energy function with respect to t is 0. It means the energy function is a constant function for every t belonging to the closed interval 0 to t. Because this is constant function, it means the value of this function, that will be same at every point t belonging to this interval. So we can say that the value of E at t, where t is any point belonging to this closed interval, will be same as the value of E at 0. So let us find the value of energy function at t is equal to 0. Now to find this value, let us take x belongs to the set U. Because U is contained in U closure, so x will be a point of U closure also. And therefore, the ordered pair x comma 0 will belong to the Cartesian product of U closure and the closed interval 0 to t. And by definition, this set is the closure of ut. Now this point belongs to closure of ut. But this point does not belong to ut because ut is the Cartesian product of u with semi-open interval 0 to t. Here 0 is not included in this interval. So the point x comma 0 does not belong to ut. Now this point belongs to ut closure, but this point does not belong to ut. It means this ordered pair x comma 0 belongs to ut closure minus ut. And by definition, this is parabolic boundary of ut, which we have denoted by gamma t. So we have proved that the ordered pair x comma 0, this belongs to the parabolic boundary of ut. But on the parabolic boundary of ut, we have proved the function w is 0. It means on every point of this boundary, w will be 0. Now because this point is lying on the boundary, so value of w at this point will be 0. Now let us find the value of energy function at t is equal to 0. By definition of energy function, which we have defined by the equation 6, there we can put t is equal to 0. So that will become 1 by 2 into integral of square of curl w by curl t at the point x comma 0 plus dw mod square. Here dw we have taken as at the point x comma 0. Now we can use the result which we proved above, that the value of curl w by curl t when t is 0, this is 0 because the point x comma 0 belongs to the Cartesian product of u with the set t is equal to 0. Also dw, that is 0. Therefore we can say that the value of energy function at t is equal to 0 is 0. Now energy function was a constant function, means the value of energy function that was same at every point belonging to this interval. And because the value of E at 0, that is 0, so we can say that the value of energy function is 0 for every t belonging to this closed interval. By definition, energy function is half of the integral of curl w by curl t square plus square of mod of dw. Now this integral is equal to 0. Now the integrand in this integral is a non-negative function, and if the integral of non-negative function is 0, then the function itself is 0. So this integrand will be 0, and this is true for every t belonging to the closed interval 0 to t and for every x belonging to u. Now again, these two quantities are non-negative quantities, and sum of two non-negative quantities is 0. It means both of them are individually 0. So this term will be 0 and also this term is 0. From here we have obtained partial derivative of w with respect to t is 0. And from here we have obtained dw, that is 0. And these are true for every x belonging to u and every t belonging to the closed interval 0 to t. So we can say that the function w is independent of x and t. It means the value of function w at the point xt, that will be same as the value of function w at the point x comma 0. But at this point, value of function w, that is 0. We proved it already. So we can say that w at the point xt, that will be 0. And this is true for every such point belonging to the set ut. Now, by definition of function w is u minus u bar. So we can say that u minus u bar is equal to 0 for every point xt belonging to ut. So we have proved that u is equal to u bar. This proves the uniqueness of the solution of the given initial value problem for the non-homogeneous wave equations. And this completes the topic energy methods.